Next, I want to look at a couple of applications here. And the first one is the length of a circular arc. Now, I know my picture is kind of not the best circle here, but so this is a nice circle, and we have a central angle. So this vertex here is right at the center of the circle, and of course, R is radius. So R is the radius of your circle. Theta is going to be the angle that's created. But using this formula here, it does have to be non-negative, so we're going in the positive direction. And we strictly talk about radian measure here. So if you have something that's in degrees, you're going to have to convert it to radians first. Then what happens is we can find the arc length of that circle by using the following formula. So S, which is the arc length, so that pink part right here, how long that part of the circle is given by the radius times the angle. So let's look at an example here. So let's say a circle has radius, we'll do 20 inches. Find the length of the arc intercepted by a central angle of 120. So the first thing to note here is that our theta is 120 degrees, but this formula works with radians. So I do have to change this over. So think back how we change that over. We take that 120, we multiply it by pi over 180 to give us the result of radians. 2 zeros are obviously going to cancel, and then 6 divides both into 12 and 18. So you have 2/3 or 2 pi over 3 radians. And then I can find that length. So my R theta is going to be 20 inches times the 2 pi over 3. And you don't need the radians anymore. Your final part will be actually in inches. So whatever that radius is, that will be your units. If it was feet, it would be feet, etc. Here, I don't really have much simplifying to do. I can multiply straight across. So I have 40 pi over 3 inches. Now, that would be the exact answer. So if you need something exact, that would be it. If you need the decimal approximation, I am going to go to my calculator here. Okay. So this is an app that I like to use for my calculator. It mimics the TI-8384 series, but as long as you have a pi button on your calculator, you'll be fine. So I have my pi button right here. So I'm going to do 40 times. And then for me, because it's in yellow, I'm going to hit that yellow button first. So second pi. I like to hit enter, and then I'm going to go ahead and divide it by 3. And I get about 41.89 inches. Okay. If you don't have pi on your calculator, then you can go ahead and just use this here. I would use all the decimal places though. I wouldn't just use 3.14. You're going to have a lot of rounding error if you do that. So again, make sure your calculator has the pi feature, but if it doesn't, then you want to use 3.141592654. Use all those decimals to ensure that you have a more accurate answer. If you don't, I guarantee you off. So if I did 40 times just 3.14 and divided it by 3, I'm getting 41.87. So if I'm rounding to decimal places, that would be incorrect. So you want to use extra decimal places if your calculator does not have a pi feature on it. The next application I would like to talk about here is linear and angular speed. And before we start, there's a nice excerpt in your text that really provides an example about the difference between the two. So let me read that to you. It says, a carousel contains 4 circular rows of animals. So think about a carousel or a merry-go-round. A lot of times there's more than one row. Maybe not 4, but there's usually at least 2 or 3 where there's like an inner row and then the outer row, for instance. As the carousel revolves, the animals in the outer row travel a greater distance per unit of time than those in the inner row, right? So if you think about a carousel, right, on the inner circle, it's a tighter circle, so you're not traveling as far, whereas on the outer circle, they're traveling, a longer distance as they go around that circle. So the animals on the outer row have a greater linear speed than those in the inner rows. By contrast, all animals, regardless of the row, complete the same number of revolutions per unit of time. So all animals in the four circular rows travel at the same angular speed. So angular speed is about the revolutions. So even though they're on different rows, the carousel is all rotating together. So they're going around the same number of revolutions. So their angular speed would be the same, even though their linear speed would be different there. So here are some formal definitions. If a point is in motion in a circle, so we talk about linear and angular speed here, we're traveling in a circular motion. So you're on like that carousel, or maybe you're thinking of, if you remember the old skip-its they used to have, you used to kind of jump around with it on your ankle. So just anything that travels in a circle of radius r through an angle of theta radian. So be careful here as we're talking about radians again, not degrees, and time t. Its linear speed is given by the following. So you have v. V is often used for velocity, which is speed. So it's given as s over t. S is the arc length that's being created. Again, t is time. And it also has an angular speed, which has to do with revolutions, how many times it's going around the circle per minute, per second, however it is. And that's given by this here. This is a Greek letter. It looks like a W. It's actually a Greek O called omega. And that's given by the angle theta for time. And there is a relationship between linear speed and angular speed. So your linear speed is the angular speed, but multiplied by the radius. So if you have one, you can find the other and kind of bounce back and forth pretty quickly. They do have a relationship there, but they're not the same. So your linear speed is the angular speed, so that revolutions per minute idea, or per second, times radius. So let's look at an example. Again, I'm so sorry. A wind machine used to generate electricity has blades that are 10 feet in length. So think about when you have wind energy. If anyone gets out to the MAT163 Gardner campus, we actually have 2 windmills. So you can see it in action. And those blades rotate around. Excuse me again. So those blades are moving in a circular motion as they go around. And in this example, I'm not sure about the ones at the MAT163, but in this example, the blades are 10 feet long. The propeller is rotating at 4 revolutions per second. So it's going around 4 times per second. That's actually quite quick, so it must be a windy day. And in this case, we want to find the linear speed of the tips of the blade. So we're looking for the linear speed in this case. Now, if you know the revolutions per second, you actually know the angular speed. So we know that the omega is 4 revolutions, and that's per second. So a lot of times what we'll do, we have this word per, it means division. So 4 revolutions per second, and if it's per second, it's per 1 second. So we'll often set this up as a ratio. Now, everything has to be in radians though, so I can't really work with this yet, so I need to change this over to radians. And what you want to remember if you think about radians is that a full revolution around the circle is 2 pi radians. So 2 pi radians is the same thing as 1 revolution. And I'm doing something very specific here. I'm setting up ratios so that my units will cancel. I don't want revolutions. Obviously, that's helpful in the real world and talking about what's happening. But if I'm trying to find my linear speed, I need things in terms of radians. So I need to get rid of this revolution idea and convert it to radians. So I put my revolution on the bottom so that it cancels with the one on the top. And now I can multiply straight across, and I get 4 times 2 is 8. So I have 8 pi radians. And then obviously 1 times 1 is 1 per 1 second. Or we can just write per second at that point as well. So now for our linear speed is the arc length over t. But I don't have arc length here. I can also use the formula of radius times my angular speed, right? So because of this association, there's different ways to get the linear speed. If I knew the arc length, I could just divide it by the time. Or what I could do here is I'm using that r theta instead for arc length. I take the radius and I multiply by my angular speed. So my linear, this was my angular speed, is equal to the radius times this value. My radius here is 10 because if you think about this as a circle, your radius is going out 10 feet. Those blades are 10 feet long. You can see there's that circle being formed, right? Kind of going right around there. So our radius is 10 feet. And then we're multiplying that by 8 pi in 1 second. Now, when we go ahead and we find linear speed, we don't need to include the radians here. That kind of gets dropped. So what's happening is you have 80 pi feet per second. And 80 pi, if you usually calculate, is about 251 feet per second. So that's the distance that those outer tips, that's what we're looking for, those outer tips are traveling. So they're traveling 251 feet per second, which would be 4 revolutions. But that linear speed, again, depends on where you are. If you weren't 10 feet out, if we were only 5 feet out, maybe I wanted to figure out how far this point was traveling. Well, you're only multiplying by 5 now. So your linear speed does change depending on where you are in that circle. The further out you are, you're increasing that linear speed, even though everything's traveling the same number of revolutions. So it's kind of a complex idea to think about the fact that something traveling in a circular motion has different kinds of speed, right? It has that angular speed, which is the revolutions per second, per minute, whatever it is. And then it also has a linear speed with how far different points of the object are traveling as well.